Hi, here's another problem involving beat frequency. One of the easiest things to do. It's just the subtraction. So, beat frequency is equal to F2 minus F1, or F1 minus F2. It doesn't matter. It's just the difference between two things. So here's a problem for you. A violin that is not properly tuned produces a frequency of 447 hertz when the violinist tries to play the note A of frequency 440. How many beats per second are heard when a properly tuned piano simultaneously plays the actual in-tune note A? And then part B, if the 0.560 gram per meter string has a tension of 60 newtons, what new tension is needed to get the string in tune? All right, so what do we know? We have out of tune, so our initial out of tune, I'm just going to say out, was 447 hertz, and the piano, the in-tune piano, is 440 hertz. That's all we need to do to answer part A. How many beats per second are heard when a properly tuned piano simultaneously plays the note A? Well, 447 minus 440. That is 7 beats per second, or 7 hertz. Same thing. But I often like beats per second just to remind myself that it's a beat frequency. It's not an actual frequency being produced by something. It's the beat frequency that we hear because two things are close together and we're hearing both. Well, that was easy. Okay, here's the second part. If the string has a mass per unit length and a tension, what new tension is needed to get the string in tune? All right, so we have a mass per unit length of 0.560 grams per meter. And I look at that and I say, grams. Okay, need to convert to kilograms. So 1,000 divided by 1,000 to get kilograms per meter. And we have the tension when it's out of tune, so the bad one, is 60 newtons. What is the in tune tension? How much do we have to change the tension to get the string in tune? All right, how can we do this? Well, we have tension in one whole equation. Must be this one. All right, so here we are looking for the tension. We have the mass per unit length, but that means we need to know what our speed is. What is the speed of the wave on the string? All right, so I think, well, okay, the other equation, V equals frequency times wavelength. We're looking for this. We do have the frequency, and we don't know this. We need the wavelength now. Well, that's not going to help because we don't know the length of the string. So, must be another way to solve it, huh? All right, so let's see. We want the new tension. We want this, we need this and this. Okay, and there's that, and well, we do know, if I look at these two, I know the mass per unit length, the linear density, and I know the out of tune tension. Okay, with those two, I can get the out of tune speed. Can I do anything with that? Well, yeah, because if I know the out of tune speed and I know the out of tune frequency, I can get the wavelength. Okay, I can get the wavelength. So the way I'm going to get the wavelength is from this equation. That's going to be coming from this equation. So this is out of tune. Okay. Right. Let's give it a try. So for out of tune, I'm just going to do, it's the square root of the tension, 60 over the linear density, 0.00560. And if I do that calculation, what do I get? I get 327.3 meters per second. It's pretty high. It's a fair bit of tension on that string. Oh no, it's a really heavy string. Okay. Now, so there, I'm going to here, so out of tune equals the out of tune times the wavelength. My wavelength will equal the speed over the frequency, 327.3 over out of tune frequency, 447. Okay, so my wavelength is 0.732 meters. Is that reasonable? So, 73 centimeters, so something like this. Yeah, I would say that's reasonable. Okay, now this doesn't change. We're not changing the length of the string. We're not changing which harmonic it's in. So this is just going to stay the same for whatever we're playing. So I know this is staying constant. And that is what we needed to do this. All right, so now I can figure out for in tune. Okay, so V for in tune would be the frequency in tune times my wavelength. In tune frequency is 440 times 0.732. All right, so my new speed for in tune is 322.2 meters per second. And again, I like to stop here and say, does this make sense? We went down in frequency, and so if the wavelength stays the same and this goes down, the speed should go down. Did it? Yes. We started at 327, now we're at 322. It makes sense. Great. So now we can get our in tune tension. And using this equation here, V squared would equal T over M over L. And then just pop that M over L to the other side. So V squared times mass over length. 322.2 squared times the 6. I'm running off the edge there. My in tune tension then is going to be 58.1 newtons. And don't just stop there. Check to see if the answer is reasonable. So we wanted the frequency to go down. So to have the frequency go down, we need to have the speed go down. If the speed goes down, the tension needs to go down. Did it? Yes, we went from 60 to 58. And again, it's 7 hertz that we're changing by. So a small change in the tension does seem reasonable. Now this is one way to solve this. There is another way to solve it where you don't have to go through and figure out the wavelength. It's just saying, well, how much did it change by? So let me erase and show you the second way to solve this problem. Okay, so the second way to solve this problem, we want to know what the new tension is, the tension in tune. We know the out of tune tension. We know the out of tune, I don't know, that's 60. We know the out of tune is 447, and the in tune is 440. Okay. We can connect these variables together by connecting the two equations that we're dealing with together. We have square root of tension over mass per unit length. We also have velocity is frequency times wavelength. All right, so they're both velocity equals. That means tension over m over L is equal to frequency times wavelength. Now I have an equation with tension and frequency in it. What else is in the equation? Well, mass per unit length, that's a constant. The linear density, how thick and heavy the string is not changing. We're not changing the string. The wavelength is also a constant because, again, we're not changing the harmonic, we're not changing the length of the string, so that's it. This means that the square root of the tension is proportional to the frequency, or tension is proportional to frequency squared. If the frequency is changing by a factor of 440 over 447, so what's the ratio, what's the factor by which the frequency is changing? So the frequency goes down by whatever this amount is. That means the tension is going to go down by that amount, 440 over 447 squared. Tension goes as frequency squared. So if you do this, the in-tune tension should be the out-of-tune tension times this ratio, 447 squared. Pop a 60 in there, and it ends up, we get exactly the same answer that we got before, 58.1 newtons. And it was a lot less calculation. And so I'm a lot more confident that, yeah, this is the answer, because I really just did one calculation, whereas the other way I had to do a bunch of calculations. So this is kind of a nice way to solve the problem if you're comfortable with the proportional reasoning. You know, you got to say, how do these relate? Well, if the square root of the tension is proportional to the frequency, then the tension is proportional to frequency squared. We don't really care about all that other stuff because it's constant. So there's another way to solve this, and choose whichever one makes the most sense for you. I hope it was helpful.